metal. Now let's explore the effect of cooling rate on permeability and how it impact porosity in die casting. The cooling rate play a crucial role in determining the secondary dendrite arm spacing, which is the distance between the secondary branch of a dendrite that formed during solidification. Higher cooling rate result in a smaller SDAS, while lower cooling rate produce larger SDAS. SDAS stand for secondary dendrite arm spacing. Okay, so higher cooling rate reduce SDAS, leading to smaller feeding channels in the mushy zone. As a result, permeability is lower because the gaps between the solidified grains are smaller and less interconnected. Lower cooling rate create a larger SDAS, resulting in a larger feeding channel that allow molten metals to flow more easily, hence increasing permeability. The diagram on the left illustrates this concept. On the left, with low cooling rate, we see a larger solid grains and more significant liquid metal channels, indicating higher permeability. On the right, with a high cooling rate, the solid grains are more tightly packed and the feeding channels are smaller, indicating lower permeability. Permeability, denoted by K, is a measure of how easily molten metal can flow through the semi-solid region. The formula on the slide show that permeability depend on the liquid fraction and SDAS. The graph on the right show how permeability change with the different cooling rate. At a higher cooling rate, 0.1 degree centigrade per second, permeability is significantly lower compared to the slower cooling rate, 0 degree centigrade per second. This indicates that the controlling the cooling rate is essential for managing the permeability and thus the porosity in the casting. By optimizing the cooling rate, we can control the size and distribution of the porosity, leading to the higher quality casting with fewer defects.